So if you press here, this pressure doesn't have anything to do with this cell. Right? So this cell is not active. In order to activate this cell, the pressure should occur here, inside the receptive field. So we call this area receptive field, the area of the skin which is covered by the branches of a fiber. Okay? So any stimulation inside the receptive field may activate the cell, outside the receptive field may not activate the cell. Right? Another thing which is important here is that in the central region, we have more branches. In the peripheral region, we have fewer branches. So we can say that the sensitivity of a receptive field in the center is more, but in the peripheral region is less. Right? So when the sensitivity is less in the peripheral region, it means we need more powerful stimulation to activate the cell. But in the center, we need weaker stimulation to activate the cell. Another thing which is important here is that there is an overlap between the receptive fields of two fibers. So there is an overlap here, overlap here, overlap here, right? So for example, in this overlapping area between these two fields, we have more branches. So, I mean, we have some branches from this cell, other branches from this cell. If we stimulate here, and the stimulant is powerful, then we can expect that both of these fibers are activated. But if the stimulation is small here, is weak here, then these fibers are not activated. Right? So receptive field is part of the sense organ. Here is the skin. Part of the skin which is innervated by the fiber, and the stimulation inside this area may activate the cell, but the stimulation outside cannot activate the cell. So this is the receptive field. Got it? Now, based on the receptive field, we have two important concept here called temporal and spatial summation for activation of a receptor. So it's similar to temporal and spatial summation in a synapse. Similar to that, so there we had actually combination of EPSDs or IPSDs together, but here we have these principles for coding of the sensory stimulation, I mean the intensity of the sensation. Okay, so let's see. Actually, the synapse is the gap between two neurons, okay, but here we don't have two neurons. We have one neuron and the skin.
So what is receptive field?
Receptive field is the area of the skin innervated by a fiber. Okay, so any fiber has its own receptive field. So, if we have, for example, 100 fibers that innervate the skin, then we will have 100 receptive fields. So one for each fiber, right? And these receptive fields have some overlaps. Okay? Some of these receptive fields are larger, others are smaller. Good? Okay. So, we have a pinprick to the piece of the skin here, and this skin is innervated by parallel fibers, sensory fibers, so each of them have its own receptive field, right? So, imagine that this stimulation is weak, okay? And it may activate some receptive fields. Okay, so a receptive field here. So we may have have another receptive field here. And another receptive field here. So let's clean the branches. Okay? You can see 3 receptive fields. First one, second one, and third one. Now, we have a pinprick to this part. Right? So it's located in the peripheral region of this receptive field, the peripheral region of this one, and the center of this one.
Yes.
Right?
Yes.
I told you that. Imagine that this stimulation is very weak. Then, how many fibers will activate that?
A lot. Very a lot.
So we have only 3 fibers.
So, 3.
All of them.
All of them are activated?
It's weak?
The one.
Yeah, it's very weak.
So just the one.
No, just the
What's the
center
one?
one.
The one and the second.
Yeah. This one, which receives the stimulation in the center. But because the stimulation is weak, and this is happening in the peripheral part of this receptive field and peripheral part of this one, these 2 fibers are not activated. So only this one is activated.
Yes.
So when the stimulation is weak, only one is activated. But how? I mean, what about the stimulation that is very strong?
Okay, all of them.
All of them will be activated, right? The central part is activated because the stimulation is strong. This one is also activated, and this one. So 3 are activated. So the number of fibers activated in a nerve depends on the stimulation intensity. If the stimulation is weak, only a few fibers are activated. If the stimulation is strong, then more fibers are activated. Right?
Yes.
So we have the same concept here. Strong stimulation activates several fibers. Moderate stimulation activates moderate number of fibers. And weak stimulation only activates a few fibers. Right? So imagine that these nerves carry the signal to the brain, and the brain is on the top and sees that few fibers are active. It means stimulation is weak. When it sees that a lot of fibers are actually bringing the action potential to the brain, then it can interpret that the intensity was strong. Right? So we call this spatial summation. The number of fibers that are activated actually signify the strength of the stimulation. Another one is temporal summation. I told you before that if you press the pacinian corpuscle weakly, then a few channels are open, receptor potential is small, firing frequency is low.
Yeah.
Right?
Yes.
So, you increase the pressure. More channels are opened, frequency of action potential increases. So the frequency signifies the intensity, right? So, action potential from a single fiber. Sometimes it's very low, I mean the frequency. Sometimes it's very high. When it's low, it means stimulation is weak. When it gets higher, it means the stimulation is strong.
High.
So we call this temporal summation. So 2 ways for sensory coding, coding of the intensity of the stimulation of temporal summation, firing frequency of action potential in a fiber. The second way is spatial summation, activation of higher number of fibers. Right? So this way we can, the brain can interpret the intensity of the stimulation. So, sample question. by increasing the intensity of the stimulation or by increasing the pressure on a pacinian corpuscle, which one increases? No, let's change it. Okay. Which of the following signify that the stimulation is stronger?
Yes.
Okay? Change in the amplitude of action potential. 2. Change in the threshold of action potential.
No.
3. Change in the frequency of action potential.
Yes.
Yes, yes.
4. Change in the duration of action potential. I told you before? Yeah. Anything else? Okay, so we have 3 options. Which one is the correct answer? Frequency of action.
Yes.
Okay? Another type of question. Which one signifies a higher intensity of stimulation? Okay? Let's say activation of the thickest fibers in a nerve, activation of the thinnest fibers in a nerve, activation of unmyelinated fibers in the nerve, activation of higher number of fibers in a nerve.
High number.
Easy to see,
Like
right?
myelinated,
Yes.
sir.
Yeah.
Like myelinated and
Yeah, it's not related actually, okay? Because when we talk about the receptor, for example, imagine a pacinian corpuscle, it always uses a beta fiber. It's always myelinated, okay? So, activation of myelinated fibers or unmyelinated fibers is not a mean or is not a tool for coding the intensity of the stimulation. Only these 2 are ways for coding the intensity. The number of fibers, frequency.
Frequency. Yes.
Okay? So, scheme, receptive fields in the scheme, receptors in the scheme, different fibers. Okay, we have seen these. So they bring the information to the spinal cord. Soma is in the DRG, the central process coming to the dorsal horn of the spine. Okay? Here we have another concept called neuronal pool. Okay? So far we have seen only connection between 2 neurons. Okay? But now we want to go beyond this. Okay? So we have seen that the receptor in the skin brings the information to the spinal cord. What happens in the spinal cord? Do we have one neuron which has synapse with this neuron goes off? Usually no.
No.
Usually we have several neurons that goes. So we have a neural pool here, a collection of neurons.
Plexus.
So the information from a single incoming neuron spreads to a large number of neurons in the spinal cord. And the arrangement of these neurons are important for us. So now, let's focus on this. So when we talk about neural pool, we need a collection of neurons that receive the information from a single neuron. Right? So, examples. The entire cerebral cortex is a neural pool. So we have billions of neurons in the cerebral cortex. They receive information. The arrangement of these neurons is important for processing of the information. Okay? I mean, arrangement means wiring. Type of connection between these cells. Because for every action or every function of the brain, we need a neural network, not a single neuron. Okay? So network is important. Network means the type of connection between the cells. So the basal ganglia, nuclei of the thalamus, cerebellum, mesencephalus, pons, medulla, dorsal horn of the spinal cord gray matter. All of these can function as a pool. And they have their own special organization. So let's see a simple example. So you have neuron number 1, which connects to neuron A, B, and C. You can see the branches. They make contact with neuron A. Some of them go to neuron B. A few of them go to neuron C, but there is no connection between 1 and D. Right?
Yes.
And here you can see the second neuron number 2, that has more synapses on neuron B, a few synapses on neuron C,
And no,
few synapses on neuron B, but no synapse on neuron A. So we have 2 input neurons and 4 output neurons. Input neurons bring the information, output neurons
Three.
actually
Can
carry the information, carry the information out of the neuron.
Yes.
Right?
Yeah.
So, consider neuron 2, it has a stimulatory field. Stimulatory field means neurons that receive information from this one. Okay? So, in this stimulatory field of neuron 2 includes neuron B, C, D. Stimulatory field of neuron 1 is neuron A, B, C. So in a stimulatory field, some neurons receive a lot of synapses, others receive a few synapses. Right? So imagine that you have one action potential here. This action potential comes here, goes this way and this way. And then this way, this way, this way. So when it comes here, one action potential is converted to several action potential. Right? Each of these generates its own EPSP. Right? So we will have several EPSPs in this neuron, a few EPSPs here. So summation of EPSPs here is very large, but summation here is small. Right? Now we can say that if you have one action potential here, for sure neuron D is also activated.
What?
Neuron D is also activated because it has a lot of EPSPs, they combine together, they change the potential to the first. So this one is activated. But what about neuron B and C?
No.
They
Maybe.
receive only a few EPSPs.
Maybe they were.
Maybe they are activated, but usually because they are
A few.
only a few fibers or a few EPSPs, the summation is
Yes.
not
No.
enough.
Actually.
So neuron D receives suprathreshold activation or suprathreshold stimulation. Neurons B and C receive subthreshold stimulation. Suprathreshold, subthreshold. Subthreshold stimulation is also called facilitating. What do I mean by facilitation here? So, neuron B and C receive actually a few fibers. They will have a few EPSPs, they combine. Potential changes, but it doesn't reach threshold. Okay. What happens if neuron 1 is also activated at the same time of neuron 2? Then neuron B and C receives some activation from neuron 2, some other activations from neuron 1. Okay? So, before stimulation from 1 comes to these neurons, it had some change of potential toward the threshold, but it was subthreshold.
Something.
Now, stimulation from neuron 1 come here and it's superimposed on the simulation that were there before. Okay? So they combine and it can reach the threshold. So they are activated if both neuron 1 and 2 are activated.
So,
Okay? So the concept is that you have input neuron, output neuron, the connection is different. You have a stimulatory field, sometimes it's also called distribution field. All neurons that receive fibers or branches of a fiber. Okay? In the stimulatory field, some neurons receive suprathreshold stimulation, other neurons receive subthreshold or facilitatory stimulation. Okay? So, the input neuron makes several branches, so we call this stimulatory field or distribution field. The central region of the distribution field has more branches, so neurons located here receive more branches, so they receive suprathreshold stimulation. We call this discharge zone, the zone that neurons are activated if input neuron is active. Right? The peripheral region is called facilitated zone. Neurons here receive subthreshold stimulation. They can be activated if they receive other stimulations from other inputs. Right? So, central region is more sensitive. And if this input fiber is inhibitory, then we don't have discharge zone and facilitated. The whole region is inhibitory. Right? We don't have facilitated zone because the stimulation is inhibitory. The cell is inhibited. Right? We have combination of or summation of IPSs. But the central region shows more inhibition. Peripheral region shows less inhibition. Got it? Any question here?
No.
yes.
Yes?
What about two facilitated zones combined to each other to innervate specific nerve? Maybe it will be action potential in this nerve, isn't it? Two, by
Two
combined.
facilitated zone. Yeah, you mean overlap of facilitated zone.
Not supra. Yeah, not supra.
Yeah, so we can consider that the facilitated zone of this neuron
And the second neuron has that zone?
has some overlap with the facilitated zone of a second neuron. So when both of them are activated, the facilitated zone is activated. So, but for activation, it needs stimulation from two sources.
Yeah, two sources.
Yeah. Okay. So now let's see some of these networks. Actually, these are simplified networks. Okay. So the first one is called divergence. So you can see that the input neuron is divided into two branches. Each of them activates another neuron. So again, these neurons make two branches. They activate two neurons, and so on. Okay. So action potential from one neuron spreads over a lot of fibers. So we call this divergence.
Divergence.
It's a type of amplifying divergence because one action potential is amplified in this network. So the result is several action potentials in several neurons. Right? So amplifying divergence. The second type. Again, we have divergence. So parallel fibers come to the pool. They activate two different populations of neurons. Some of these neurons go this way. Others send their axons to the other way. Okay? So action potential from one source go toward two different targets. Right?
Yes.
So again, we have divergence, but into multiple tracks. Examples, in the dorsal column of the spinal cord, fibers go
Cerebellum.
either to cerebellum or to thalamus. Right? Okay. Another type of arrangement convergence of signals. So you can see that fibers from a single source, so several fibers from a single source merge together on the output neuron. So one single neuron receives several fibers from one source. So we have convergence from a single source. But another type is convergence from multiple sources. So from source 1, source 2, source 3. So from different sources, neurons come to the cell, and this one can combine all of these signals together. What do we call this?
Multiple.
Yeah, I mean from our previous session, I told you that this is called integration. Integration. Okay, so example is like this. Anterior motor neurons in the ventral horn actually receives some information or some fibers from interneurons. So they are located in the intermediate zone of the spinal cord brain network. But these interneurons receive fibers from peripheral nerve fibers, propriospinal fibers, corticospinal fibers, and other descending pathways. So from several sources, signals come to the interneurons carry the signal to the motor neuron. So we have combination of these actually signals. So we call this integration. So it's a convergence network or convergence circuit. Okay? So convergence from different sources. Another type of circuit is reciprocal inhibition circuit. One input fiber comes to the pool. It has two branches. Branch 1 directly activates output neuron number 1. But branch 2 activates an interneuron, which is inhibitory, and this interneuron inhibits neuron number 3. So we have two output neurons. The first one is activated directly, but the second one is inhibited by way of an inhibitory interneuron. So one action potential in input fiber activates one neuron, inhibits another one. Right? So we call this reciprocal inhibitory circuit or reciprocal inhibition circuit. So an example. You want to walk, right? So you want to bring your leg forward. You want to step forward. Okay. For this movement, some muscles should contract, other muscles should be relaxed. Okay? So the brain sends signal to the leg. First to the spinal cord, then from the spinal cord to the leg. Okay? Basically, we need two versions of signals. One signal for activation of agonist muscles, another signal for inhibition of antagonist muscles. But the brain doesn't send two signals. It only sends one signal. The signal comes to the spinal cord, one single signal. Okay? Then it goes into a circuit like this. Agonist muscles are activated directly. Antagonist muscles are inhibited by way of an interferon. So neuron from the cortex come to the spinal cord, activates alpha motor neuron or motor neurons to agonist muscle directly, inhibits motor neuron to antagonist muscles by way of an interferon. So we call this reciprocal inhibition circuit. Okay, another type of circuit is reverberatory circuit or oscillatory circuit. This is for prolongation of a signal. So input neuron here brings the action potential to the pool. It activates output neuron, but the output sends the collateral back to the soma of itself. Okay? So action potential activates the output. Output sends the action potential back to itself. So one action potential goes this way, another one goes this way. And this one activates the cell again, and again, and again. Okay? So, if the input is activated, the output will be activated repeatedly. So the signal is prolonged.
Okay.
Right? So, this one is more complex. So we have an input neuron, an output neuron, and several interneurons. So between the input and output, right? So we have collaterals from the output and collaterals from each of these interneurons. And we have another interneuron that sends the axon back to the interneurons. So action potential arrives, activate this interneuron, this one activates this. Action potential goes this way and this way. So we have some backward action potential. And when it's activated, this one activates. It also activates the interneuron. And again, we have cycling of action potential in the neuronal. So one action potential from the input activates the circuit. And the circuit will actually continue to fire action potential more and more. Okay? So the same circuit is here, but you can see other incoming fibers. So we have input, output, interneurons, and facilitator neurons, inhibitory neurons. So they are coming from different sources, right? So imagine that a neuron which is facilitatory activates these synapses. I mean, increase the sensitivity of these synapses, right? Then, when the input neuron brings the action potential here, these synapses are ready to pass the signal to the next one very fast. So the entire activity here increases.
Can you repeat it again, please?
Yeah. So we have connection between input and output by way of some interneurons. So there are several synapses in between. Right? So these synapses can be facilitated by some neurons or can be depressed by other neurons. If a facilitator neuron increases the sensitivity of these synapses, then when action potential arrives from input, it can go through the synapses easily and it can reach the output very fast. So the whole activity increases because the synapse is very ready to be activated, right? But if an inhibitory interneuron depress or suppress these synapses, then we need more APSPs, we need more summation, right? So the probability of activation here decreases. So the passage of action potential from input to output decreases. So the number of action potential in the output decreases, right? So we have the same circuit here, but instead of only having one input and one output, we can have several parallel input fibers, several parallel output fibers, and also parallel interneurons. Okay? So we have connection between input and output, but the system can decide about the number of incoming fibers and the number of outgoing fibers, right? So in some state, I mean other neurons that come from other sources may decide that, okay, only one output is activated. So this input activates this interneuron, this one, and this output is activated. In another time, maybe we need more signal, powerful signal, I mean. So a lot of these incoming fibers are activated. So they activate the interneurons, and the interneurons activate a lot of output fibers. So we will have actually lateral spread of the information in these segments. Okay? So one way for prolongation of a signal is using oscillatory circuits or reverberatory circuits. Another way You're familiar with that from the previous session. For a synapse, I told you that there are two types of neurotransmitters.
Small molecules,
Small molecules, large molecules. Large molecules,
How long act for a longer time?
longer time. So if you have release of, for example, substance P, then its action on the postsynaptic neuron actually persists more than the short molecule neurotransmitters, right? So we have prolongation of the action. So two ways for prolongation of an action is using a long-acting neurotransmitter to using a reverberatory circuit. Got it?
I have a question.
Yes.
About the oscillatory circuits. When does it stop? Because after the action, the potential becomes slowly less and less, and then it stops like that.
Yeah. So we have fatigue of the synapse here. We will see this in other slides. Okay. So sometimes we have fibers from other centers that come to the circuit and cause stop of the signal.
Immediately.
So a different source come to the signal, come to this circuit and causes a stop of the signal. Okay? So we'll see this later. Okay? So let's first see the fatigue of the signal. Imagine that we have a circuit like this one. Okay? Action potential in the input generates several action potential in the output. So the input signal activates several action potential in the output. But the action potential firing declines slowly. Then it stops suddenly. This decline is made by fatigue of the synapse. Right? So these synapses are tired, gets tired, and they decrease the firing activity in the output. Okay? When it reaches a threshold, a critical value, then the passage of the signal through the synapse stops suddenly. Okay? This one. So, this one. But imagine that the facilitatory neuron is active. Then the synapses are facilitated. So fatigue happens later or slower. So we have more action potential and fatigue happens later. But if we have inhibitory neuron that suppresses these synapses, then the firing activity declines faster. So fatigue happens soon. Right? So, sometimes in some places in the brain, we have continuous activity. An example is the center for breathing. So we start breathing in our fetal life, and we continue to breathe until death. Right? So we have continuous activity of some neurons, and this activity happens during the sleep, during the exercise, okay? Every time, continuously, non-stop. How this happens? We have two possible mechanisms. One is that some neurons in the CNS have a pacemaker activity. You know pacemakers. So the kinetic of the channels in the membrane is different. So we have continuous leak of ions into the cell. So the resting membrane potential is not fixed. It shows progressive increase until it reaches the threshold. The threshold causes action potential, then the resting membrane potential declines to a trough. Then again, we have the leak, and it goes up, and the second action potential is made. Okay? So one way for having continuous activity is having a pacemaker property. The other one is a reverberatory circuit. So you can think of a reverberatory circuit that functions, in time, okay? It always functions and it never stops. So if we consider a circuit like this, okay? So an action potential comes here and causes repetitive output. So this way, by this reverberatory circuit, we can say that action potential in the output continues non-stop, right?
So how can we stop synaptic after discharge?
Sorry again. How?
Can we stop synaptic after discharge?
After discharge.
Yeah.
So after discharge means the action of the neuropeptide, right? I told you before that the neuropeptide binds to its receptor, opens a channel, for example. After that, it is protolyzed or it diffuses out of the synapse. So the action is terminated, right?
What about the fatigue of the synapse in this case?
Yeah, fatigue of the synapse. In this case, yeah, you mean for continuous
Yeah, for
activity?
continuous.
Yeah, maybe we have some circuits that are not exposed to or that are not subject to fatigue. Okay, they can regenerate themselves very fast. So, okay, so continuous activity here for breathing. Sometimes the action of this reverberatory circuit increases, some other time it decreases. So this way breathing can increase or decrease, okay? Yeah, the rhythmic signals again for breathing. So it may be generated by a reverberatory circuit. So, for the stability of this neuronal circuit, he asked me, okay, we have other sources that cause stabilization of the circuit by way of inhibitory signals that are sent to the circuit. So some inhibitory circuits cause the stability of the neuronal circuit. For example, we have basal ganglion neurons that always send inhibitory signals. Another way is synaptic flexibility. And the last one is that sometimes the sensitivity of the synapse is increased by upregulation. Okay. Other times it decreases, and we call this downregulation. So a synapse can increase or decrease its stability for passage of the signal. Okay. So the action of a synapse is not a fixed action. It can regulate itself. Okay? So upregulation usually happens when we have increased expression of receptors in the postsynaptic cell. Okay? So a presynaptic cell releases neurotransmitter onto the postsynaptic cell. We have some receptors for the neurotransmitter. Right? So imagine that we have 3 postsynaptic receptors. The neurotransmitter can only bind to 3 receptors.
Yes.
So one action potential generates one action potential here. So now, imagine that in some specific state or condition, we need to increase the action of this synapse. Then, the synapse can increase the number of receptors. Right?
Yes.
So, a higher voltage EPS is made. And the transition of the signal from this synapse increases.
Increase.
One action potential generates 2 actions.
Two action potential.
So we call this upregulation. Some other time we need to decrease
Decrease.
the sensitivity of the at synapse. So we can remove some of these
receptors.
receptors. So two action potential here,
One.
we generate one action potential. So the sensitivity of the synapse.
Yeah.
So one way for up-regulation and down-regulation is changing the number of receptors. Right? Some other time, you may have sprouting. You know sprouting? So, for example, it has 3 branches on this cell. Now, it sprouts so
More
it sends
branches.
more branches. So, again, we have up-regulation.
Up.
Another way is the sprouting of the dendrites. So a cell had a kind of connection with the postsynaptic cells. So there were 5 branches of the dendrite. Now we need more activity. So we have sprouting of the dendrite. So we will have more dendrites. Right?
Yes.
So we can change the sensitivity of a receptor by changing the number of postsynaptic receptors, the number of dendrites or branches or the spines, you know, a spine of dendrite, number of dendrite may increase also, or the number of axon terminal. Right? So that's all about the synapse. We can have our next session at 1 p.m. Is that okay?